also going to change. And the way we write it now is, it looks kind of weird, we get the kinetic energy is gamma minus 1 times mc squared. We need for this to reduce to the old expression for kinetic energy at small speeds, and we can't do it directly. If gamma is 1, we would put in 1 minus 1 and we'd get 0. So we need an approximation that works at low speeds. And this is something, again, you'd get in, I think, a second semester calculus class in this case. We could have Mathematica do it for us and give us what's called a series expansion, or an approximation, at low speeds for gamma. And we do it, so we tell it expand it around 0, and we get these various terms. Now we have to decide how many of these terms are we going to keep and how many we're going to throw away. If we already know that beta is close to 0, we might say, well, okay, beta squared is even closer to 0, we can throw this away, and all the higher terms. If we throw all that away, we're saying kinetic energy equals 0, so that's the limit of no speed. This is too approximate. So we have to keep at least this term in the expansion. When we do that, if we write this minus 1, we get, we have the 1 plus beta squared over 2 minus 1. That just gives us beta squared over 2 mc squared. How could we write that? Well, we could say beta is v over c. So let's plug that in. So now we're saying ke, again, this is an approximation, beta squared over 2 times mc squared, but that's 1/2 times v over c squared times mc squared. That gives us 1/2 mv squared, which is what we expected. So it does reduce to regular old Newtonian kinetic energy. The connection between total energy and momentum in relativity is yet another change. So what we used to have is Newtonian kinetic energy was p squared over 2m, or 1/2 mv squared. Now what we have is something called total energy. That includes momentum, as well as this mass-related term. We can rearrange this now that we know that mass is the thing that never changes, and write it as m squared c to the 4th is e squared minus p squared c squared. Now, because of the fact that we defined P as mv gamma, we could do some algebra and say that the total energy E is mc squared times gamma. Remember, kinetic energy was gamma minus 1 times mc squared. The big difference here is, compared to the Newtonian case, you still have a value for energy even if something is not moving. So in your own frame, where you say my gamma equals 1, I would say I have no kinetic energy, but you still have energy present, and that's the rest mass energy. So that's E equals mc squared. This is that famous equation that Einstein is associated with. We would get it from this by saying, okay, there's no momentum because it's in my frame. So this disappears. E squared is m squared c to the 4th, or E equals mc squared. This is a crazy amount of energy associated with every little bit of mass. It means 1 kilogram of mass is equivalent to about 9 times 10 to the 16th joules. The real equation, instead of E equals mc squared, though, should be E equals mc squared gamma, or the big one here. Now, the big idea here is even though mass is invariant, it's not conserved. It can change in time. This is absolutely crazy in terms of our regular experience. In chemistry, they have what they call the law of conservation of mass. And what that tells them is if you have 23 grams of sodium and 35.5 grams of chlorine, you put them together and you get 58.5 grams of salt. Now, in reality, you combine these two things, about 800 kilojoules of energy will be released, which is kind of a lot. That energy has to come from somewhere. If you want to separate this salt back into sodium and chlorine, you have to dump 800,000 joules of energy into it. What this is telling us is we don't really have quite 58.5 grams. We have that minus this energy over c squared. This is 9 nanograms, or 9 billionths of a gram. So even though it's not really a law, it's obviously going to be pretty darn useful in chemistry if you can say we're correct to better than a part per billion by saying mass is conserved. In any chemical reaction, if we could measure the masses of both the products and the reactants, extremely accurately, we'd see they aren't exactly equal. And the difference is the energy either released or absorbed divided by c squared. Even for very energetic chemical reactions, explosions, whatever, they're not energetic enough to notice this change in mass. Nuclear reactions are about 1,000,000 times more powerful than chemical reactions, though. If you look at the first atomic bomb dropped on Japan, the energy released was 63 trillion joules. That's about the equivalent of 15 million kilograms of TNT. The bomb itself only had a mass of about 4,400 kilograms, maybe like a large truck or SUV. If you were able to pick up all the tiny pieces of that bomb that were, driven all over the area by the explosion, what you would find is all the tiny pieces together would weigh less than 1 gram less than the starting mass. So mass is almost conserved in these reactions. That means destroying an entire city was done by the release of energy equivalent to the mass of a paperclip. So mass is a ridiculously efficient way to store energy. You can also convert mass to energy on a small scale, like in the chemical reactions, or on a large scale, like in a PET scanner at a hospital. In this kind of scan, and we'll look at these later, you have radioactive material that emits positrons, which are antimatter electrons. These positrons, when they're emitted, find electron partners and they completely annihilate and form two gamma ray photons. Big particle accelerators, like you see in the news every so often, like the LHC over in Europe, they run that kind of process in reverse, where you dump a lot of energy into something and you have it create matter in the collision.